Hi, my name is Jamie de Jong. I created this video, Infinite Limits of Rational Functions, for the course MAT135 at the University of Toronto. By the end of this video, you should be able to calculate limits of rational functions at infinity by factoring out dominant terms. And we'll see what that means through a couple of examples before finishing with some exercises for you to practice. So we've got our first example here. You can see we have a rational function. We have a quadratic polynomial as the numerator and as the denominator. And we'd like to take the limit as x tends towards infinity. So based on other calculations of limits for rational functions, your first instinct might be to see what happens to the numerator and the denominator as x tends towards infinity. So let's do that first and see what happens. So if we first take the limit as x tends towards infinity of the numerator, well, we have 3x squared minus 6. As x tends towards infinity, the 3x squared term tends towards infinity, and subtracting 6 doesn't have any effect on that. So this limit goes to infinity. What if we look at the denominator? So here again we have a quadratic. We have 4x squared plus x plus 2. As x goes to infinity, 4x squared and x both go to infinity, and the plus 2 has a negligible effect. So again, we get infinity. And well, if we think of this as a fraction, the question is really, what can we do with something that is infinity divided by infinity? And the answer is not a lot really without knowing more about the functions. Perhaps one of them goes to infinity twice as quickly, and then the answer is either 2 or a half, depending on which one it is. But maybe one of them actually tends to infinity significantly more rapidly, and then perhaps the entire limit goes to 0 or infinity. We don't know from this calculation. So we actually have to approach this rational function as a whole, rather than breaking it down into the numerator and the denominator. So what can we do? Well, instead, we factor out the largest power of x in the denominator. And that is the dominant term that I referred to in the learning objective. So in this case, the largest power of x in the denominator is x squared. So we're going to factor out the x squared term in both the numerator and the denominator. So the limit we have is the limit as x goes to infinity of 3x squared minus 6 divided by 4x squared plus x plus 2. And if we factor out the x squared in the numerator, we have x squared multiplied by 3 minus 6 divided by x squared. And in the denominator, we have x squared multiplied by 4 plus 1 over x plus 2 over x squared. And, well, we can cancel out these x squareds. So we're left with the limit as x goes to infinity of the other factors. So 3 minus 6 over x squared divided by 4 plus 1 over x plus 2 over x squared. And this is equivalent to the limit that we started with. How does this actually help us? Well, now what we can do is we can actually evaluate the numerator and the denominator as x goes to infinity, and we won't get infinity anymore. So this will give us something slightly easier to deal with. So as we take x to infinity, the 6 divided by x squared tends towards 0, and in the numerator we're just left with 3. And in the denominator, 1 divided by x tends to 0, 2 divided by x squared tends towards 0 as x goes to infinity, and 4 is the only thing we're left with. So this limit is equivalent to 3/4, which was not something that was obvious just from substituting x equals infinity in. So the technique we've used is to factor out this x squared, which will give us a constant term, at least in the denominator. In this case, it gave us a constant term in the numerator as well. It might not always, and we'll see that in the next example. But it enables us to guarantee that our denominator is something we can actually evaluate. And you'll also see this, we can also think about this as dividing by the dominant term. So in this case, we divided every term in the fraction by x squared because x squared was the largest power that appeared in the polynomial that was in the denominator. Okay, so here I have a slightly different example. It has a square root in the numerator, which makes it seem a little bit more complicated, but essentially we can still do the same thing. So again, the highest power of x in the denominator is x squared, so we're going to factor out the x squared. And when we do that, well, in the numerator, we get x squared times 1 minus 3 over x squared. In the numerator, what do we have? Well, we'll figure that out. We know we'd like to factor it out, so we'll have to figure out what that actually means. We can still cancel out these x squareds. So what happens when we have this 1 over x squared multiplied by a square root? Well, we can bring the 1 over x squared inside as being essentially the square root of 1 divided by x to the power 4. And the numerator works basically the same as the previous example. So now in the numerator, well, we have still a square root, but we have x cubed divided by x to the 4 is 1 over x. And then we have x divided by x to the 4, so 1 over x cubed. And we already know what our denominator looks like. So now we can consider what happens to each of these polynomials as x goes towards infinity. So what do we get? Well, 1 divided by x goes towards 0. 1 divided by x cubed goes to 0. So the terms inside the square root tend towards 0. The square root of 0 is 0. And in the denominator, we have 1 minus 3 over x squared. 3 over x squared tends towards 0 as x goes to infinity, so we expect that to be 1. We have 0 divided by 1, so this limit is 0. So despite the square root, we still followed exactly the same process here. We divided by the largest power of x that appeared in the denominator. You just have to be a little bit careful with the square root about how this division actually interacts with the terms inside the square root. Okay, so we've covered 2 examples now of how to factor out the dominant term in the denominator to be able to find the limit of infinite limits of rational functions. So I'll leave you with a few exercises to practice this. There's a variety of different ones here. They all look a little different, but they do all use the technique we learned in this video. If you have any questions, feel free to discuss them on Piazza or to come and talk to me in my office hours. Thank you.